In this video I'm talking to people who know how to differentiate 3x to the power of 4 with respect to x. We know that it's simply times by 4 here to get 12x, subtract 1 from the power, so we get 12x cubed. We're going to be differentiating things like 2x minus 1 squared, 3x minus 4 to the power of 7, and things of the same structure. At the moment, you can all differentiate all of these anyway. So we might say, well, if this was 2x minus 1 squared, if y was 2x minus 1 all squared, we can expand that. So that's 4x squared minus 4x plus 1. And then differentiating that is pretty straightforward. Times by 2, subtract 1 from the power, 4x differentiates to minus 4. Now that's all very well, but it gets a bit more complicated down here. This is the same as x plus 1 times x plus 1 times x plus 1. There is a neat way of doing this using a binomial expansion, but let's do it longhand. We'd say it's x squared plus 2x plus 1 times x plus 1, which is x cubed plus 2x squared plus x squared plus 2x plus 1, which is x cubed plus 3x squared plus 3x plus 1. I'm a bit bored of this already, but still we're getting there, getting the answer. Dy dx equals 3x squared plus 6x plus 3. To be honest, my mathematician brain is telling me this isn't very elegant. There must be a neater way of doing this. And that's what we're going to be learning today, because there's no way I want to take 3x minus 4 to the 7 and expand that. I'm going to be looking for a quicker way of doing this. The aim of this video is that you watch it, you understand the structure of what I'm going to be talking about, and you get to the stage where you can go into the lesson next time able to differentiate things like this using the rules I'm going to teach you. And I also want you to have thought about some questions I'm going to ask, which you'll then discuss in the lesson. All of these are what we call functions within a function, and I'm just going to give you this rule for now. If we're differentiating dy dx, where it's a function in a function, it's dy du times du dx. Now there are lots of proofs for what this means and why it works. They are interesting, but they don't really add to your understanding of the of actually how this process works. So I would encourage you, if you want to look at the proofs, go ahead and do that. We can just talk through one very quickly here, but it's by no means essential to the Maths Methods course. Now let's consider y, which is a function g of u, and we'll consider u as being a function of x. So what we're saying is that y is g of f of x. That's what we're really saying here. Y is g of u is f of x. So y is g of f of x. It's a function inside a function. Now we know that delta x is a small increase in x, so we can also consider delta y as being a small increase in y, and delta u as being a small increase in u. Now we already know that dy dx is the limit as x approaches 0 of delta y on delta x. And using, well, without going into too much detail, using a bit of dodgy fraction technique, we can say, well, this is actually the same of x, limit of x tending to 0, of dy delta y on delta u times delta u on delta x. Now, I haven't really explained that, but hopefully you can see that that sort of works. The next step, which again I'm not going to explain why it works, but the limit of these two things multiplied together is the two limits multiplied. That is to say, it's the limit as, should have delta x here, limit as delta x approaches 0 of the first thing times the limit as delta x approaches 0 of the second thing. Now, that in itself, I haven't explained the step, but just go with it for now. If you're interested in why it works, you can ask your teacher or Google it. And this is the same. Delta u approaches 0, delta y, delta u times the limit, x approaches 0, delta u, delta x. Which, going back to our initial notation, is the same as dy, du, du, dx. I'm going to keep saying it. It's not essential that you follow that proof, but you need to know that it has come from somewhere. And you need to have this idea that in all of these cases that we looked at before, we have a function inside a function. We have this function 2x minus 1 inside the function of x squared, or inside the squaring function. This one over here, the inner function, is x plus 1, and that's inside the function x cubed, or something cubed. So we've got that inner function and an outer function here. Again, in this case, the inner function is 3x minus 4, and the outer function is something to the power of 7. So we've got a rough idea of a proof of why it works, or at least a belief that a proof exists. Now I'm going to show you the procedure. When using the video, you need to watch this as many times as you need to follow what's going on. I'm going to set it out using a structure which I recommend you follow exactly. So, I'm going to start with this one. Y equals 2x minus 1 squared. As we said, this is a function inside a function. So I'm going to call the inner function u. This is the same as something squared. Just take a moment to see why that's the case. And if this is true, well, it must be true that u equals 2x minus 1. What I'm going to do, I'm going to have two columns of working here. I've got the left-hand side, which is kind of my main story, the main line of what I'm doing. Then the right-hand side is auxiliary to that, just doing any extra bits which come up. So we know that u equals 2x minus 1. The formula I'm using is dy dx equals dy du times du dx. This means, this part here, differentiate y with respect to u. Well, that's fairly straightforward. Usually we expect an x here, but we're differentiating u squared with respect to u. That's just 2u. To get du dx, that means differentiate u with respect to x. Well, I'll go back over to my right-hand side here, and I'll find du dx, let's see, is 2. So this is 2u times 2, which is 4u. Now, a general thing in maths, we like to give things in the form in which they were presented. We're dealing with y's and x's. This u is just an extra thing which we brought in. So once we've used it, we've finished with it. Let's switch it back out. We know that u equals 2x minus 1, so we'll call that 4 lots of 2x minus 1. And we could expand that to get 8x minus 4, which, if you remember, is what we got last time. In fact, in this case, this little procedure probably takes longer than just expanding the brackets, but you'll see it's going to be much more useful as we go on. Now this one's a bit more involved. Y equals x squared minus 1 to the power of minus 4. First thing we do is identify the inner function, the thing which is having a further function applied to it. So this is u to the power of minus 4. Okay, the last thing that's happening is to the power of minus 4. So that's our outer function. If that's the case, then we know that u must be x squared minus 1. I'm going to write down the formula each time I do this. dy dx equals dy du times du dx. dy du is minus 4u to the minus 5. du dx, well, I'll go over to the right hand side and I'll sort that out. du dx is 2x. So I need to times this by 2x. So this is minus 4. It's u to the power of minus 5, so that's going to be u to the 5 on the bottom of a fraction. And I'm going to switch out u for x minus 1 to the power of 5 again, times 2x, which is minus 8x on x squared minus 1 to the power of 5. Now, that's the procedure you need to be able to master in time for the next lesson. So you need to watch that video as many times as you need to and be really clear about every single step. Why has it happened? What have we done? How are you going to do it again? These are the questions you're going to be asked in class. These first 4 here, differentiating them, should be completely straightforward. The next 2, fairly straightforward. We always like to look for patterns in maths, so looking at the first 2, you might start to see a pattern or a shortcut which, as you get really fluent with the chain rule, will let you skip some of the lines of working, or at least be able to perform a mental check to make sure you've done it right. And in looking for that pattern, which is really cool when you see it, you're going to differentiate x plus a to the power of n, and then bx plus a to the power of n. See if you can work out what that pattern gives you. Now these next 2 questions you may well struggle with. I'd like to know which of these 3 functions, one on the square root of 2x minus 1, x plus 2 to the power of 7 times x minus 4 to the 5, and e to the tan of x, which of these are chain rule situations? They are not all chain rule situations. And if you think they are, have a go at differentiating them. Finally, if f of x is sine x, then I'm just going to tell you for now, the differential of that is cos x. Now if we know that, using the chain rule, what is the differential of sine 2x? What happens when you differentiate sine 2x?